So I highly recommend you to write down your notes today. Otherwise, everything becomes like a tongue twister. You don't know exactly what we're talking about. All right? So today, we're going to go back to the first section, 9.1, to talk about what would happen when our sample is not representative of the population. As a result, we draw incorrect conclusion. That's along the line with the election we've talked about earlier. What happens if the survey you've collected are coming from a specific group? They're willing to. You're not proactively picking and choosing your sample. They choose to report their preference in your survey, right? So it's really hard to get a representative sample and have a accurate projection of what the election is going to be. But in our world, in the engineering world, the data we've collected are most likely coming from your experiment, your process, and your stuff. So those numbers are much more objective and helps you with much higher confidence. Okay, so let's look at, Tarlar, Galushan, can you be my facilitator today?
Yeah, sure.
Thank you. All right, and also, Tarlar, remind me, let's start with that in case I forgot. Okay, I want to go back to here because last time we showed you how to use Excel to perform a hypothesis testing. Now I want to show you how to use Minitab to perform a hypothesis testing. Okay, and then we'll start type 1, type 2 error. Okay, let's start with this one because this one we didn't get a chance to go over last time. So let's go over this exercise using Minitab. Okay. In this question, we are collecting oxygen concentration in 20 different dams around Tennessee area. So this 20 observation is listed over here. Okay. Then the water quality engineer is interested to know whether the testing data supports the claim that the dissolved oxygen concentration is exactly 2.5 milligrams. It's exactly 2.5. All right. What else do we know? They've collected 20 samples. Population standard deviation is given. Okay, so I'm going to write down the hypothesis testing, and then we'll take you to Minitab. So we're performing hypothesis testing. That mu is exactly 2.5. And while the alternative says that it is not 2.5. Based on this, we know it's a two-sided hypothesis testing. What else do we know? We also know the population standard deviation is 2.07. Based on this information, we know this is going to be a z test. We're going to calculate a z statistic. Sample size is 20. All right? Have those information in mind. I will take you to Minitab. Okay, so Tarlar, we should be looking at my Minitab window.
Yeah.
Okay, great. So I'm gonna clean it up. Okay, so I have the numbers summarized over here. 20 data points, oxygen concentration. We're performing a hypothesis, two-sided hypothesis testing to see if this oxygen level is exactly 2.5 or it's not. So I'm going to stat basic statistic. Okay, I'm going to pause here for a sec so you have time to write this down. It also tells you about 95% of all the analysis we've covered this semester is going to be under stat basic statistics. Okay, all the graphical summaries or all the numerical statistics are here. here is our hypothesis testing, even it doesn't say so. Okay, in our case, population standard deviation is given, so we are going to do a one sample z-test. If it's not given, we're going to do a t-test. If the population standard deviation is not given, we'll do a t-test. Two sample t and pairs are chapter 10. We'll go over that in chapter 10. So the only one that is not going to be under basic statistic is our chapter 11, regression. Okay, we'll get there in 2 weeks. All right, so let's go to the z-test. Okay, you can choose different ways to summarize your data. In our case, our data is listed over here. Okay, we're going to select our data. Let's summarize in the C4 column. Population standard deviation is given, 2.07. We're performing hypothesis test. Testing value is listed over here. That's our null hypothesis. Let's go to option. Option allows you to set up your alternative hypothesis and also your alpha. Our alpha is 0.05, so the confidence interval is 95%. Okay, if you click on this drop-down menu, you do have the option to set up a two-sided or one-sided hypothesis testing. Okay. All right, let's perform the analysis. Okay, the session window, the analysis is on top of the screen, and that's really all you got. There's nothing more. Okay, the basic descriptive statistic of the data you've reported, number of data, sample mean, sample standard deviation, 95% confidence interval, our null hypothesis, our H0 and H1. And all the value reported here are your test statistic and p-value, which is the probability under the standard normal distribution that's greater than your test statistic. So what's missing here? Critical value is not given to you. Okay? Critical values are not given to you. If you recall from our hypothesis testing, there are two ways to draw conclusion. First, compare your test statistic to critical value. The second one is to draw conclusion based on your p-value. What do we compare p-value to? To your alpha. Okay? So, Minitab is a professional statistical software. Okay? It allows you to perform hypothesis testing on one population, which is what we're doing over here, two population, which is what we'll do in chapter 10, and multiple, more than 3 population hypothesis testing, all at the same time. So you don't really need to derive the critical value of all of this hypothesis testing. All you need to know is to derive your p-value, compare the p-value to your alpha. If it's less than your alpha, reject the null hypothesis. Greater than the alpha, fail to reject the null hypothesis. All right, so that's one feature in Minitab. It does not give you critical value. Okay, so you really need to have a clear understanding of hypothesis testing before you choose to use Minitab. Excel is not any better because it doesn't really have a lot of structure in there. You have to go through each steps on your own. So both becomes very powerful when we perform multiple population hypothesis testing, which we'll cover next week. Right?
Yeah.
So this is all you get.
Minitab a lot better for population statistically wise. Which would be better, a better system to use, Minitab or Excel?
So from our class perspective, both are equally useful. When it comes to other analysis that beyond our class, Minitab does offer a whole lot more function over here. Okay, if you take more on engineering statistics, each one of this module is one class. That just tells you how powerful Minitab is. But it's irrelevant for our class. Because in our class, for the scope of work we've discussing this entire semester, Minitab and Excel does exactly the same thing. So it's a matter of what you're more used to.
Okay. Because I'm gonna take a class that is specifically writing this using Excel or Minitab, so that's what I was asking.
Yeah. So hopefully after the semester, you have a taste of which one. What is your preference? And you just go ahead, stick with that software and continue. Okay. Let's go back to here. Let's go back to my OneNote. I want to show you another example that we did last time. We also went over this time. This is their white blood cell recovery days. Okay. So here we have 19 patients, and we're reported their white blood cell recovery days. The hypothesis testing is the mean recovery days exceeds 12 days. All right. So this is a one-sided test. We have it on the right already. One-sided upper bound test. Population standard deviation is not given. All right. So this is going to be a t-test. This is going to be a t-test. Oops. Okay, let's go to Minitab. All right, I have the data listed in my worksheet. All right, here are my 19 data points. Let's perform the hypothesis testing. The hypothesis testing value is 12. Population standard deviation is not given. So in this case, we're going to perform a t-test. Okay. Data is listed over here on my C2. Hypothesis testing. Test value is 12. Let's go to option. Here, it allows us to set up a one-sided testing. Okay, alternative hypothesis is that the mean recovery day is greater than 12 days. Let me double check on alpha. I believe alpha is 0.05. Yeah, 0.05. Okay, so I'm going to keep this as a 95. I don't need any graph. Let's not generate graphs. I don't need that at this point. Okay, same thing, very brief results. All right. One-sided hypothesis test. Alternative is set up as a recovery date greater than 12 days. P-value greater than 0.05. So we fail to reject the null hypothesis. Fail to reject because p-value is greater than alpha. Okay, how do we know? You shouldn't have to memorize it. Go back to our notes last time, and instead of comparing the location of your test statistic to your critical value, compare the area under the bell curve, under your normal distribution curve of the test statistic, and compare that to your alpha. You should be able to draw a conclusion pretty easily. Okay, so real quick, that's what I want to cover on Minitab. Okay, let's go over to our hypothesis testing error. All right, even this book start introducing type 1, type 2 error as early as section 9.1. But I really feel like you need to know how to perform a hypothesis testing properly, so you know what will happen when you make a mistake. Why will you make a mistake? Just like the election example we've talked about before. The sample you've collected are not representative of the entire population. How likely would it happen? very unlikely, but that probability is not zero. Because it's not zero, that's why we're addressing it here. It's considered as a risk of how reliable your data is. Okay, so to address that risk, let's look at table 9.1. Okay, on the left-hand side, this column over here, this column over here is from your hypothesis testing result. From your hypothesis testing, there are only two ways to draw a conclusion. You either fail to reject H0, or you reject it. Only two possibilities. Okay. Now we need to compare that with our reality. There are only two realities. My H0 is either true or false. Here's the part students get really confused. Why do we know the reality? If we know the reality, why do we still need to perform the hypothesis testing? Okay, the reality is given to you as a comparison. Okay, we need to know the reality, so we know if our hypothesis testing is making a mistake or not, and therefore we can derive the probability of making that mistake. Okay, so I would highly recommend you to either work on the slides or have your notes ready so you can remember. Okay, you can remember how do we derive type 1 and type 2 error. So here's how I want you to look at this table. All right, let's first look at this upper left quadrant. Okay, when your hypothesis testing tells you that we fail to reject the H0, which means we will conclude it. And in reality, it is true. That means there's no error involved in here. You're drawing the correct conclusion. Okay? So we don't discuss this case. We assume that's most of your case. This is the other case. The majority of the other case is here, where your conclusion is to reject the H0. You reject it, we believe it is wrong, and conclude your H1. In reality, it is wrong. So you reject it correctly. So there's no mistake involved in that. Okay? And this is, keep in mind, those two areas are most likely will happen. 90, 95%, 99% will be correct. All right? So there's a very small percentage that happens in this two area. Okay, let's start with type 1 error. What is type 1 error? When your conclusion is to reject your H0, you reject it because you believe it is wrong. So you conclude your H1. In reality, your H0 is actually true. Okay? So you're rejecting a true statement. That's when you make a mistake. And we'll refer that type of mistake as a type 1 mistake, type 1 error. Let's look at this top quadrant. Type 2 error is when your hypothesis testing tells you we failed to reject it. We cannot reject the H0, so we have to conclude it. But in reality, your H0 is wrong. You are concluding a wrong statement. That's when you make another mistake. For this type of mistake, we refer to it as a type 2 error. All right? You don't have to memorize the definition. You should have this table ready. Okay? So you can derive the probability accordingly. You know what is the definition of type 1 or type 2 error. Okay? So let's write down their definition right here. The probability of making a type 1 error, we'll refer that as our alpha. So alpha is a probability. What probability? Probability of making a type 1 error. How do we define type 1 error? Type 1 error from the table 9.1 in your hypothesis testing, we reject the null hypothesis. But in reality, your H0 is true. Okay, so here is simply rewrite the definition into probability. Let's look at 2. Type 2 error is beta. Beta is the probability of making a type 2 error. Again, what is type 2 error? In our hypothesis testing of type 2 error, we fail to reject your H0. In reality, your H0 is false. This is your reality. Okay? Keep those 2 in mind, and let's show you some example. Okay. So I'm going to rewrite the definition of alpha. Is the probability of making a type 1 error, which is the probability of reject a null hypothesis when it is true. Okay, let's give you an example. Let's say this is my sample space. I have multiple samples over here. In order to perform my hypothesis testing, I need to collect some random samples. Okay, here is my random sample average. My sample average is, I'm gonna make it as a x1 bar to differentiate from our second example. My x1 bar is 52.5. Okay, here's our hypothesis testing. We wanted to know if my population mean is exactly 50, or alternatively, my hypothesis testing is not 50. Okay, so we need to know what is our hypothesis. We also need to know what is the reality. Okay, so I'm going to write it right here. Let's say my true population mean. My true population mean is indeed 50. So the green one is a reality, and we're going to carry out our hypothesis testing. Okay, in the hypothesis testing, we are going to have a confidence interval. In this case, 2-sided, because this is a 2-sided hypothesis testing. And critical value is determined based on your alpha. So I'll just assume my 2 critical values are plus minus 1.89. How do we determine the critical value? We determine that based on our choice of alpha. Okay, determines our critical value. So these 2 are my critical value. Now let's start calculating my test statistic. Oh, sorry, I also need to give you some information. Population standard deviation is 2.5. So we know this is a z-test. Sample size is 10. Okay, now let's start testing my test statistic. I am going to put my test statistic a little bit higher right here. Okay, my sample average, 52.5, subtract my hypothesis mean, 50, divided by sigma, 2.5, divided by square root of n. $52.5. So my hypothesis value, let me see, 52, subtract 50, 3.16. So where is my 3.16? This is my 3.16. 3.16 is on the far right. This is my 3.16, my test statistic. So what conclusion are we going to draw from this hypothesis testing? My test statistic fell outside my confidence interval. As a result, we reject the hypothesis. And what are we concluding? We're concluding the alternative hypothesis that mu is not 50. All right, now back to type 1 error. Let's compare the result from our hypothesis testing to reality. Hypothesis testing tells us to reject the null hypothesis. Mean is not 50. But reality tells us it is actually 50. So reject the null hypothesis. When the null hypothesis is true, we are making a type 1 error. Okay, so I'm creating that situation for you so we can further derive the probability. Okay, so now let's start calculating our probability. Alpha is the probability to reject the null hypothesis. When will we reject the null hypothesis? We reject the null hypothesis when the test statistic is located inside the confidence interval, right? So it is the probability when it is outside the confidence interval, like that. When do we reject the null hypothesis? When my test statistic is located outside the confidence interval. Where are those areas? It's here and here. Here concludes all of the possibility to reject it. If we can derive this area, that tells us the probability of rejecting a null hypothesis. So in two situations, we'll reject the null hypothesis. When my z statistic is greater than my upper bound, or when my z statistic fell below the lower bound, plus minus 1.89. In these two situations, will lead to the conclusion of rejecting null hypothesis. So two situations will add up their probability. Okay, what does the type 1 error also tells us? My null hypothesis is true. My null hypothesis is true. This is true. In other words, my mu is 50. Mu is 50. All right? So once you identify the area, write down the equation based on the definition. The rest of them is just to carry out a calculation of a probability of a standard normal distribution. Okay, so I am going to calculate this probability from negative infinity to minus 1.89, multiply that by 2. Because in a standard normal distribution, the two areas are identical. Once I derive one cumulative probability, multiply by 2, that will give me the probability of making a type 1 error. Okay, so I'm going to jump straight to give you the answer. 28717 multiplied by 2. 0.05743. 7, and that's a 5. So what does the number mean? What does this number mean? Alpha is 0.057. This is a probability. Remember, alpha is the probability of making a type 1 error. In other words, out of the 5.74% of the random sample, collected will lead to type 1 error. In other words, we will reject my null hypothesis when it is false.
Professor, what is it? Says collective will lead to FY?
Will lead to type 1 error.
Oh, okay. Sorry about that, Professor.
No, my bad. I'm getting close to the bottom of my screen, and when my finger touches the other window of the touch screen, my other apps pops out. So trying to write it careful with the angle, and that leads to this terrible handwriting. Okay, so this is important. I want you to take a minute to write this down, this entire thing down. So I'm gonna zoom out just a little bit so you can see this entire picture. Okay, I'm gonna give you 2 minutes to write this down. In the meantime, let's discuss what is the interpretation of type 1 error. Imagine you're an engineer, you're making a product, you're performing some experiment. You want to collect some sample to make sure the product you're making is really what you believe you're making, right? So you're doing the testing, and the testing tells you you have to reject this lot because it is not meeting what we believe it is. It is not meeting the requirement of 50. But the reality is the lot you're making is actually meeting the specification. So you're rejecting a completely good lot. Okay? So type 1 error is what we refer to as a manufacturer's risk.
That's one type of error? Okay.
Yes, we're still talking about it. We're still talking about type 1 error. This part is important because calculation is a calculation, but how do we use it? Why are we deriving this risks? Because we're still drawing our conclusion completely based on a small subset of our population. So there is a risk associated with it. In this case, type 1 error is you as an engineer completely scrapping out a perfectly good product. Because let's say you're making an experiment, let's say you're making a lot of 100 product, whatever that is. You decide to pick 5 of them and test it. Within that 5, you happen to have an outlier. As a result, your sample average becomes very high. So that sample is actually not representative of this entire lot. If you simply base on this conclusion of that small subset of samples, you're going to scrap out a completely great product. So it's pretty much your money down the drain, the owner's money down the drain. So that's the risk associated with it. Is that risk high? No, it's not very high, but it's not zero. It could still happen. Okay, So in reality, how do we typically avoid this type of mistakes or this risk associated with it? Typically, make your process as consistent as possible. In other words, minimize that sigma will help. Second thing, increase the number of sample so you get a better picture of your population will help. However, if that sampling means you have to destroy the sample until you get a value, for example, tensile strength, for example, compressive strength, those are the type of tests we refer to as destructive tests. You have to destroy your sample in order to get a result. So when you're making a lot of 100, taking 5 samples, you are destroying that 5 samples. So you have 5 samples short in order to get this result. If you increase the sample size in order to minimize this risk to, let's say, from 5 to 10 samples, then you are scrapping 10 samples in order to get this result. So your sampling cost start to increase. We can just increase our sampling test by testing the entire lot. Then you end up with no product to ship to your customer, right? So there's a fine balance. How much risks are you willing to take? How many samples are you willing to so you can maintain profit and also keep your risk at a manageable level? So there's a fine balance there. As an engineer, if you know your numbers well, if you know your type 1 error well, you can play with that numbers to find a comfort area. Okay? So calculation is one thing. I do want to cover how do we use this in the engineering world. My screen just kicks me out, so let's go back. Oh, because I accidentally closed it. Okay, let's go back to that. Okay, so now I want to give you another example of type 2. Any question before we go to type 2 error? Okay. Feel free to send me a chat. I will check it from time to time. It does give me an alert, so hopefully I won't miss your question. So now let's go to beta. Okay, beta is our type probability of making a type 2 error. What is a type 2 error? Type 2 error is that in our hypothesis testing, we fail to reject my null hypothesis when in reality that my H0 is false. Right? That's the definition. Let's give you an example. Example 2 is going to be very similar to example 1, so you can compare it side by side, but I will change some parameters here. So same thing, here's my sample space. I have lots of products over here, lots of data over here, and I will randomly select a few samples here. And here is my sample average 2 to differentiate that from our first example. Sample number 2 is 50. Put together the same hypothesis testing. Mu is exactly 50. Mu does not equal to 50. Right? Same hypothesis testing, different situation. Parameters are the same. Population standard deviation was 2.5. Sample size is 10. in this situation, I will change the reality. Let's say the true population mean is 52. Okay, that's different from our example one. I want to show you how do we get to how do we make a type 2 error. All right, similar to our first case, this is our z distribution. My two critical values are plus minus 1.89. Okay. Now let's derive our z using my sample average 50. 3, subtract hypothesis mean 50, divided by sigma 2.5, divided by square root of 10. We derive that number, 50.3. 0.38. Okay, so that's my test statistic. Where is that located? It is located inside my confidence interval, slightly over the middle, 0.38. This is my, that's a 0. That's my test statistic. Okay. Well, since it falls inside the confidence interval, what conclusion can we draw from this hypothesis testing? We fail to reject the null hypothesis. Okay, as a result, we will conclude my null hypothesis that population mean is indeed 50. Now, let's take a look at the conclusion, compare that to reality. Okay, my conclusion tells me my population mean is 50, but the reality tells me no, it is not 50, it's actually 52. Okay, so we fail to reject the null hypothesis, and the null hypothesis is wrong. This is when we make a type 2 error. This happens. Let me sketch the real distribution. This one right here. Okay, in red, and I'm gonna sketch it this way, slightly on the right, because the blue distribution population mean is 50. Okay, I'm gonna extend this line right here. Okay, so the red distribution is my true population mean. Okay, it is slightly on the right hand side of my hypothesis population, but they do overlap. So there will be a small section from a red distribution that happens to fall between my confidence interval, just like this green dot here. This green dot, the sample mean, is coming from the red distribution. However, it falls on the far left of this red distribution, and it happens to be the confidence interval of our hypothesis testing. That's when we are going to fail to reject the null hypothesis and making a type 2 error. Does that make sense? So now I'm going to derive my type 2 error. Okay, so my beta is the probability when we fail to reject. When do we fail to reject the null hypothesis? when my sample average falls between the confidence interval, right? Where's my confidence interval? When my test statistic is located between plus minus 1.89. That's my confidence interval. This will lead to this conclusion. Okay? But what is the reality? This is wrong. This is wrong. My population mean is not 50. What is the reality? My population mean is actually 52. Okay? So what are we deriving over here? We're actually deriving this probability. Oops. Sorry. I want to highlight the area. So our beta is this highlighted area in red here. Everything here comes from the true population, the red population. Okay? That area, the highlight red area, is the probability coming from the red distribution, but located inside the confidence interval. Again, this is my beta. Beta is the observation, is the sample mean coming from the red population, but happen to fall inside the confidence interval. Okay? So now I'm going to get rid of the extra value. Now let's look at this plus minus 1.89. These two z-values are coming from the blue distribution. If you look at these 2 points, the 2 dots in red, in respect to the red distribution, they're not plus minus 1.89 anymore. They are 2 negative z-values on the far left side. Okay, so in order to derive those values in the new distribution, I have to convert this plus minus 1.89 into the actual value. The plus minus 1.89 is my z-value. Z-value is standardized based on a population mean of 50. Now I need to convert it back to the actual value and then standardize it again based on the red population mean, 52. Okay, here's the complicated part, but let's convert it back. Plus 1.89 is my z-value, and that is derived from an actual x1 value. Standardize it to the population mean, 50. Divided by sigma 2.5, divided by square root of 10. So my x1 value, my upper bound, is 51.5. In other words, in this red distribution, this value is 51.5. This becomes my x bar. Population mean here is 52. Okay, just to give you a perspective. The lower bound, negative 1.89, is an actual value x2. Standardize it to the hypothesized mean, 50, divided by 2.5, divided by square root of 10. Okay, so my x2 value is 48 point. So this actual value is 48.5. Okay. Now it's a matter of deriving a probability of a area. Okay. So to derive this, I will use the cumulative probability all the way to the right. I'm going to write this in red actually. That makes more sense. Cumulative probability from negative infinity all the way to 51.5. And now I'm going to standardize that to a standard normal distribution. What does the population mean in this red distribution? Okay, that's important, 52. Divided by sigma, divided by square root of sample size. Subtract the left-hand side, which is 48.5, subtract 52, divided by 2.5, divided by square root of 10. Okay. Want to highlight the differences here and here, here and here. Okay. Always know which is the population mean you're dealing with. So this is the cumulative probability to negative 0.63. Subtract cumulative probability to the far left, negative 4.43. You'll see both are negative because in this red distribution, both values are on the far left side. Okay. Negative 4.43 is way over negative 3.99. Consider that probability is almost 0. So cumulative probability to negative 0.63 in a standard normal distribution, 0.2643. Okay, let's write down the interpretation of that. Beta. This 2.2643 is a beta. Beta is the probability of making a type 2 error. So probability 26.43, a little over a quarter of the sample collected will lead to type 2 error. In other words, a little over than a quarter of the sample collected randomly will lead to the conclusion of fail to reject H0 when H0 is false. Okay, I'll give you a minute to write this down while we discuss the practical application of this. That should be good. Okay. So let's look at this interpretation of this. We believe our process is actually the blue distribution. It's the blue population. But in reality, it's already shifted to the red. So in other words, we fail to detect there's a shift in our process. What would happen if we're manufacturing something? What happens if we're making a product? We will end up, since we failed to detect it, we are going to pack it, ship it to our customer. And our customer will end up receiving a defective product. I'm sure you'll have experience with that, ordering something from Amazon, from Walmart, end up receiving a defective product. What will happen in that case? You'll have to file a return process, right? You'll probably leave a really bad review of this of the seller, right? So as there's a lot to deal with. The cost of quality when a defective product end up to the customer's end is significantly higher than you were able to detect it and stopped it before you ship it to your customer, right? So type 2 error is also considered as consumers. Consumers risk. Because we failed to detect it. It was a defective product, but we thought it's good. So we end up packing it and ship it to our customer. It is us as a customer receiving a defective product from the seller. Okay, we've talked a lot about this different type of ways to make a mistake. I'll give you some time to digest it. I will be around. Let's take a 10-minute break. Come back at 11:10. I will be around if you have any question. Okay, let's come back at 11:10.
You're welcome.
Please leave your message for 5623887.
All right, let's get back. All right, we've addressed different ways of making hypothesis testing errors and classified into two different categories, type 1 and type 2 error. Overall, if you can minimize the variability in your process, or you can increase the sample on testing, in general, it's going to minimize the risks of making either both type of error. Okay. So before we go to our exercise, the only thing, the last concept I want to cover in chapter 9 is a power. A power is the probability of rejecting a null hypothesis correctly when the H1 is true. So reject the false statement and conclude the correct statement is the power of hypothesis testing.
Professor, we still see your Google timer.
Oh, thank you. All right. Let's repeat it one more time. The last concept is power. The power of the hypothesis testing is the probability. Again, the power is still a probability of rejecting a incorrect null H0 and conclude the correct H1. It is calculated pretty straightforward. 1 minus beta. Beta is our type 2 error. Okay, subtract the probability of drawing incorrect conclusion is the power of your hypothesis testing. So mathematically, it is the probability of correctly rejecting a wrong H0. Okay? Okay, let's take a look at a few testing. Let's look at a few exercises. Okay, went over all that. Let's go to this one. Okay, we are performing experiments and calculate the heat evolved in a cement mixture. Okay, we know the population is normally distributed, and we want to know if the population mean is exactly 50. Okay, what other informations we have? This is what we're testing. We also know the standard deviation, population standard deviation. And here is your hypothesis testing. It is a two-sided hypothesis testing. Sample size is 9. Okay. Now let's go to question 8. If the acceptance region is your confidence interval, is the region that leads you to fail to reject the null hypothesis and accept it. So that's your confidence interval. If this is your confidence interval, find the probability of making a type 1 error. Okay? To start this, first, let's repeat the definition of type 1 error again. Alpha is the probability of making a type 1 error. Okay? It is the probability of reject a null hypothesis when it is true. Okay, this is our hypothesis testing. This is the reality. Okay, where in our hypothesis testing will lead to the conclusion of rejecting the null hypothesis. It is outside the confidence area, right? Outside the confidence area, which means our sample average is either greater than 101.5 or it is greater than less than 98.5. Okay. And what is the reality? The reality is that my null hypothesis is true. Population mean is indeed 100. Okay. So let's sketch this. This is my null hypothesis. Population mean is 100. Critical value 98.5, 101.5. Rejection area is here. So in other words, I am going to standardize this distribution into a standard normal distribution so I can derive the probability. Okay, this is not the only way you can derive the probability. In Excel, it does allow you to derive probability of a normal distribution without standardizing it. So there's more than one ways to derive this. So let's derive this to a sampling distribution. 101.5. I'm going to standardize it based on a population mean of 100. Standard deviation is 2. Size is 9. Less than 98.5. Subtract population mean. Standard deviation. Size. Okay. Once you have the equation established, the rest of the calculation is fairly straightforward. So probability Z greater than positive 2.25. Probability of Z less than negative 2.25. Okay. So I'm going to derive the cumulative probability to negative 2.25 and multiply that value by 2. 0.20122 multiplied by 2, 0.0244, which means 2.44% of the sample collected will lead to type 1 error. Okay, knowing the definition of the error, quantify that error by sketching a normal distribution and highlight that area. Then you can either use Excel to calculate that normal distribution directly or standardize it into a standard normal distribution. Any question? The probability is not very high, and usually less than 5% of type 1 error is what we consider acceptable. There's no question. I'm gonna move the screen slightly to the left so you can still complete.
Do you want us to put it in percentage or leave it as a decimal?
Either way it's fine. Yeah, either way it's fine because it's a probability. You can use that probability to in different ways. Either way it's fine.
Okay. Mm-hmm. Are you gonna want us to write or like of the sample collected will lead to by type 1 error?
I think what I'm going to do is to ask you what percentage of the sample will lead to type 1 error. And you can reply to either 0.0244 or 2.44%.
Okay.
Okay, let's go to the next question. B and C are very similar. Question B, find the type 2 error, probability of making a type 2 error for the case that true mean is 103. Okay, let's look at this first. Okay, let's write down the definition of type 2 error again. Probability of a type 2 error. It is the probability fail to reject a product when it's false. Consumer's risk. Okay, so we're going to go back to follow the information we derived from question 8. Assuming that 98.5 to 101.5 is our acceptance area, and we fail to reject the null hypothesis when my sample average is located within the confidence interval, right? 98.5 to 101.5. When what is my true population mean? My true population mean is 103. Okay, so let's sketch it. I'm going to sketch it right here. Okay, this is my sample average. My hypothesized mean is 100. This is how we establish the acceptance region, confidence interval, right? Upper lower bounds are 98.5 and 101.5. And where is my true population mean? My true population mean is slightly on the left, but there will be overlapped right here. Okay, this is the true population mean. So where's my beta? My beta is a sample coming from the true population, the red population that happens to fall right here inside the confidence interval. When it fell inside this confidence interval, we failed to reject the null hypothesis. And we conclude the mean is 100 instead of 103 and making a type 2 error. So the beta we're calculating is this area right here. Okay. So I'm going to go back to here. So I'm going to standardize this too into a standard normal distribution with a mean 103. Okay. So I'm going to skip a step by simply using cumulative probability to 101.5. Well, the population, the true population mean is 103. Okay, very important. You don't need to memorize this. If you can sketch this plot, you know what is the population mean in your calculation. Okay. subtract, since we're deriving a probability in a range, in an area. So I'm going to derive the cumulative probability to 101.5, subtract the cumulative probability to 98.5. And then I'm going to standardize it. Population mean in the red distribution is 103. Okay, 2 divided by square root of 9. So without calculating it, we know that both 101.5 and 98.5 are going to be two negative z-value on the far left side in this red distribution. Okay, so this will be the 101.5 is negative 2.25.
Professor, do we have to write phi instead of p, or can we just leave it with p?
Whichever.
Whichever. Okay.
Yeah. I like to slow down and write down each steps. But if you can if you can derive the area simply from the sketch, go ahead and do that. So this notation.
Oh no, just the notation. Yeah, that notation, because
This is specific to cumulative.
Oh, okay.
Probability of a standard normal distribution. Okay, so this notation is specific to a standard normal distribution and deriving the cumulative probability. So when I'm not referring to a cumulative probability of a standard normal distribution, I will always use a p. That's why you see this is the p here, this is a p here, this is a p here. This becomes a phi when I'm standardizing it into a standard normal distribution. Okay?
Yeah, because I use a p, so I'm going to change it to a phi then. Yeah, okay.
Mm-hmm. Negative 6.75. This is so far out on the left, probability is 0. So simply calculate the cumulative probability of z equals to negative 2.25, 0.0122. Go to C. Question C, very similar. Find the beta, find the type 2 probability of making a type 2 error for the case the true population mean is 105. Okay, so B and C are exactly the same thing. The only difference is the location of the true population mean. Is this beta value small than the one found in B when population mean is 103? Why? So I'm not going to sketch it. I'm not going to calculate it. I'm going to sketch it for you. Okay. Question C asks when population mean is 105. I'm going to sketch it here. Okay. Still making a type 2 error. So still the area falls within this confidence interval. So I have another population here. Mu is 105. 105 is greater than 103, so it is on the far right compared to our hypothesis mean of 100. Okay, so when it is a far right, the overlapped area of the green distribution and the blue distribution is much smaller than the red area. Okay, because it is further on the right hand side. So we know already this is my beta in question C. This green area will be smaller than the red area because again it is located further away from 100, and that long tail will leave a much smaller area than 103. What does this tell us? Remember, type 2 error is a mistake that we fail to detect when our process has shifted. We fail to detect process being shifted and not meeting the specification and send this product to our customer. Remember that? That's a consumer's risk. But if your process is shifted so far away, 105 instead of 100, we should have a fairly high probability to detect that shift in our process. Then risking it and ship it to our customers. Okay, so when it's further out, the probability of making type 2 error is much lower. So here is I wanted to write the beta. Sorry, use be consistent with our color. So the beta when mu is 103. Probability of making a type 2 error when my mean is 103 will be greater than when the beta when mu is 105. Okay, I'm not going to calculate question C. I want you to go back and practice that. Why is it smaller? Sketch your own distribution and see if that makes sense to you. But I do want to discuss the next case. What happened when my population mean is 101? When my population is 101, it is so close to the hypothesis value, right? So everything fell between these two lines all the way to here. Is going to be my type 2 error. So it is very easy for us to fail to detect such a small change in our process. Okay? So that area is going to be greater than the beta when mu is 100. Okay, again, in our practice, beta is the probability that we fail to detect a process change. When there is a very small change, a 1% of change in our process, it is very hard to detect it. When the change is 3%, 5%, it's a lot easier to detect that. The overlap area is much smaller. We should be able to collect the majority of the sample and notice my process has been shifted. If we fail to detect that, that is our beta. Okay. For that reason, since it's very hard to detect small changes, as engineers, we like to plot all of our sample over time. Okay. Another class I taught is how do we monitor, keep track of the quality. So this will be time. The y-axis will be our process, whatever the property we measure. Let's say it is our diameter. How about that? So, oh no, this one is our heat exchanged. We'll monitor it over time. So we're expecting it to be 100. and we'll measure it. Let's say we monitor it on daily basis, day 1, day 2, day 3, day 4, and you'll see the sample changes over time. As long as it's all around 100, we're fine. But when we start detecting 3 consecutive points are all above 100, that's when it makes sense to take an average and hypothesize it with the rest of the process to see if it's still within the specification or not. I've transposed this all the distribution 90 degrees because my x-axis is time, my y-axis is our heat evolved. Okay, so this is the application we use to monitor our product to minimize the probability of making a type 2 error. Okay, when there's a shift in our process, doesn't matter how small it is, we want to be able to detect it as soon as possible and make efforts to bring it back before we start making out of spec product, defective product. Okay, any question? Okay, if not, we did this one. Let's go over to the next exercise. Very similar, but this time we're going to calculate power. Okay, a manufacturer is interested in the output voltage of a power supply. Okay, we assume the power supply, the population is normally distributed. Standard deviation is 25 volts. And we're testing if the voltage is exactly 5 or it is not, two-sided. Sample size is here. We also know the population standard deviation. Okay. Question A, giving you the confidence interval, calculate your alpha. Okay, very similar to how we did it before. Let's write down the definition. Let's write down the definition of alpha one more time. Alpha is the probability that we reject null hypothesis, and null hypothesis is true. Okay, in our hypothesis testing, when will we reject it? We reject it when my sample mean is out of the confidence interval. So it's either sample mean greater than the upper bound 5, or my sample mean it's less than 4.85. When is my null hypothesis true? It is true when my population mean is 5. Okay, 2 area, we'll add them up. Okay, I'm going to standardize the first one, z greater than 0, okay, plus probability of z less than 4.85, subtract 5, divided by standard deviation, 0.25, divided by square root of sample size.
Isn't the upper bound of 5.15, not just 5?
Oh, the way I highlight it confuses myself. Sorry about that. My bad. How clear can you hear my kids screaming?
Can't hear anything.
Oh, good. Z, let me know if when it becomes a hazard. I'll go out and shut the door screaming at him. Okay, greater than 5.15, subtract 5, divided by 25 divided by square root of 8. Okay, so z greater than positive 1.7, z less than negative 1.7. Okay, so this is a standard normal distribution, cumulative. Okay, standard normal distribution, cumulative. That's when I will use this notation. Okay, all the way to negative 1.7 multiplied by 2. Point 0.4457 multiplied by 2. That will give me 0.0914. All right. Now 8.9% of sample will lead to type 1 error. Depends on your process. If I were the engineer, 8.5% seems a bit high for me. So I'll definitely go back and take a look at my samples. Okay. Second case, find the power of the testing for detecting a true mean output voltage at 5.1. 5.1 and 5 are so close to each other. So before we derive this calculation, we know beta is going to be very high, and the power is going to be really low because 5 and 5.1 are so close to each other. Okay. Let's go over here. Beta Beta is the probability of a fail to reject. We fail to detect the change in our process when fail to reject H0 when H0 is false. Okay, let's sketch it. This is my sample average. I'm going to use question A from the acceptance area. Acceptance area is 4.85 to 5.15. 4.85 to 5.15. And where's 5.1? 5.1 is so close to it, right? Make this a little higher. So this one mean is 5. This one mean is 5.1. All right. So what is the area we're deriving? It is the area under this red distribution that fell within the confidence interval between 4.85 to 5.15. So, let's see here.
Professor, why is the curve so close to the other, so close to the line where the 5.15 is at?
Because one is 5.0, the other one is 5.1.
Oh, okay.
Scale-wise,
Oh,
they're
okay.
so close to each other. So
Oh,
the
okay.
question is trying to prove a point that when you're only moved by 0.1, it is very hard to detect that change. As a result, your beta, your beta is going to be very high. It's highly possible to fail to detect the change.
Okay.
All right, so it is the probability. Fail to detect means my X bar sample average is inside the confidence interval. It is between 4.85 to sample average to 5.15. My H0 is wrong because the true population mean mu is 5.1. All right, so this is what I'm going to do. I'm going to erase my hypothesis value. Okay, and calculate this highlighted red area. That is my beta. This is my beta. Okay, so probability, let's standardize it. 4.85 subtract the mean. What is the mean of this process? It's not 5 anymore. Very important, knowing what is the population you're deriving. The population mean is 5.1. It's very important. Okay? Divided by sigma, divided by square root of n. .15 standardized to this red distribution.
What do you want? What? I don't know what you
So I'm going to derive two cumulative probability. Um, 5.15 is 0.566. Subtract cumulative probability to the left. Negative 2.83. In other words, more than 70% of the sample collected from this red population will fall within this confidence interval. As a result, we will not be able to detect the shift. And that 71% is really high. In other words, in this case, we're deriving a power. The question asks us to derive power. Is 1 minus beta. The ability to correctly reject the incorrect null hypothesis. So the ability for us to draw the correct conclusion is very low, 0.2867, less than 30% of the chance to call this shift, this very minor shift in our process. Okay, so that's all I wanted to cover today. There's no test next week. We're going to start chapter 10. Once we wrap up chapter 10, the quiz will, quiz 5 will occur the week after. Okay, we're getting very close to the end of the semester. Almost there. Hang on tight. All right. that's the end of our course for this week. I will see